Section 1.8 is combining functions using polynomial and rational functions. So here's a bunch of definitions. Copy down the essence of this. You don't have to copy every single word. Sum, difference, product, and quotients of functions. If f and g are two functions with intersecting domains, that means they share x values, then for all values of x in the intersection, the algebraic combinations of f and g are defined by the following rules. So if we want f plus g of x, it's the same thing as taking the f function separately and adding it to the g function separately. The same thing with subtraction. The same thing with the product, and the same thing with the quotient. The difference here is that we need to make sure that g of x does not equal 0. In any other operation, g of x can be 0, but not for a quotient. So basically it says that if we want to add two functions together, we take the functions individually and add their values. In each case, the domain of the new function consists of all numbers that belong to both the domain of f and the domain of g, and as noted, the zeros of the denominator are excluded from the domain of the quotient. So we'll get into doing some work with this in just a second. Copy that part down. All right, so here are two functions. We're going to call this, get a pen out. This will be our f function, and kind of funky color over here, this will be our g function. Oh, I'm missing some of my graph. There we go. So put those two functions on your notes, and we're going to do some composites with this. So f plus g of 3. As we said, this is going to be f of 3 plus g of 3. I apologize, I don't have my good stylus with me, so it's going to be a little bit hard sometimes. I'll try and keep it as neat as I can. So f of 3, so on the f function, I go over to 3 and I see that that is 0. On the g function, when I go over to 3, I see that it is -1. So f plus g of 3 is -1. F minus g. So this is going to be f of 2 minus g of 2. So again, on the f function, when I go to x equals 2, I see that the function value is 1. G of 2, the function value looks like -1 to me, so we're going to get 0 for that. Oops, oh, bad mistake. Take a look, see if you can tell what I did wrong. This was supposed to be subtraction, so minus a -1 gives me a value of 2. Keep my operation right. Okay, multiplication, see if I can do this one right. F of -3 times g of -3. So f of -3 looks like 1 to me. Multiply that. There's a parentheses here. G of -3, 1, 2, 3 looks like 2. So that would be 2 also. And I think I did a quotient. I've got f of 0 divided by g of 0. F of 0 is, let's call that -1. G of 0 is 2, so -1/2. So composite functions, or just combining rather, not composites, combining functions using the operation and using the value from each function individually. Okay, so given the following functions, let's now find some composite functions using a function definition rather than a value. So it asks us to determine domain. So the first thing I'm going to look at is the domain of each individual function. The domain of f of x, for f of x, the domain is that x has to be greater than or equal to -1. Remember, we cannot have negative values under a radical. The domain for g of x is simply that x cannot equal 0. So those are the domains of my functions individually. Okay, so let's now look at some composites of these two functions. So let's do f plus g of x. So that means I am going to simply take f of x, which is the square root of x plus 1, and add it to g of x. So now I have a new function. I don't even have to simplify that. So since the domain for f of x has to be greater than or equal to -1, but cannot have 0, my domain here, using our interval notation, I'm going to say that it goes from -1 to, from -1 to 0, non-inclusive, combined with 0 to infinity. This textbook writes this, what to me is a little bit odd, and I prefer the notation that I just used. They say that the domain is from -1 to infinity minus the set of 0. I think that this notation makes a little more sense. We go from -1 to 0, but don't include 0, and then we pick up on the other side of 0 and go to infinity. So this is, again, this is what the book says. I would prefer the interval notation that I did on top. All right, division. So this one, I'm going to take my f of x function divided by my g of x. Now this one I can clean up a little bit by multiplying by the reciprocal. So this would be the square root of x plus 1 times x over x minus 1. And again, we'll call that x root x plus 1 over x minus 1. So let's talk about the domain here. Again, all of my domain restrictions from before apply. The function value in the composite cannot include any x values that were not in my original domains. However, we now also need to exclude x equals 1. So again, the way the book writes this is that we're going from -1 to infinity minus the set of 0 and 1. Interval notation, this is going to get a little bit messy this time. Theirs is a little more concise. But again, I'm going from -1 to 0. And then I'm going from 0 to 1, but I've got to skip over 1 before I go on to infinity. So I've added a restriction to my domain because of the fact that I have a new denominator. So combining using addition, multiplication we did, division we did, and we got two new functions with some new domain restrictions. Polynomial functions. This is a fancy way of writing that a polynomial function is something with numeric powers and always represents integers. And in this case, it's going to be actually integers greater than or equal to 0. And so it's powers. So an example of a polynomial would be 3x cubed plus 2x squared minus 4x plus 3. So you notice that the powers decrease all the way down to, this would actually be x to the 0, which is just 1, so that would be my last term here. And we just name the coefficients in front with the same subscript as we do the power. That's a fancy way of writing a general polynomial function. We need to know that. The degree of a polynomial is determined by the term with the greatest power. So this polynomial, the first term is third degree, powers, second degree, this term is first degree, and the last term is 0 degree, but the degree of the whole polynomial is a third degree. So for our example, we have a third degree polynomial. Zeros, real roots, and x-intercepts are all the same thing. They are the value of y, should be a v, value of y when x equals 0. So in other words, we plug in 0 for x and we find out what y is. That will give us something called zeros, real roots, x-intercepts. They all mean the same thing. Oops, sorry, we'll go back. So once you've written that down, I'm going to erase so that you can read my next thing. Graphs of polynomial functions can be determined in part by their degree. Polynomial curves of nth degree have no more than n minus 1 turns. So if we have a polynomial that looks like this, that's a first degree. So it has 0 turns. Oh my gosh, sorry, this is a really bad pen. We have 0 turns. In other words, this is a line. Think about our parabolas. This is a second degree. I apologize for this. Let me try that one again. I need to write slower with this pen than I usually do. So this is a second degree polynomial. It can have at most 1 turn, and that holds true of our parabolas. Let me just quickly put an example of something like y equals x to the 4th power, and we'll just cut it off there. That's a 4th degree. It can have at most 3 turns, so it's going to look something like that, 3 turns. It might have fewer, and we'll talk about how we figure that out later. So rational functions are the quotient of 2 polynomial functions. Domain is restricted by any values that would make q of x equal to 0. So x, when plugged into the q function, cannot create a 0. Rational functions have what's called asymptotic behavior. They have asymptotes. Vertical asymptotes are values that make the function undefined. In other words, that they make q of x 0. So any value a that would make the denominator 0 would create a vertical asymptote. So let's say that this is a value a, and it would make q of a 0. If q of a is 0, I get a vertical asymptote. So the graphs are going to look things like this. Horizontal asymptotes represent the end behavior or the value that the function approaches as x is very far from 0. So horizontal asymptotes look something like this, and as I go out and out really far to the right from 0 or really far to the left from 0, I would approach this b value, and that would be my horizontal asymptote. I know you've worked on this before. So let's graph this. First thing I want to do is simplify, and we may be adding something a little bit new into this for you. I'm sorry, let me factor this numerator. So the factors of the numerator are x and x minus 1. The factors of the denominator are x minus 1 and x plus 1. So this will simplify to x over x plus 1 as long as x does not equal positive 1, because the factor that I took out, if I plug in plus 1, I will get an undefined value. So this is true everywhere except at x does not equal 1. Now let's look at our horizontal asymptote. Horizontal asymptote. As x gets further away from 0 or approaches plus or minus infinity, this function gets very, very close to the number 1. As x gets bigger and bigger and bigger and bigger in this function, this little plus 1 doesn't really make much difference. So when x is 1,000,000, 1,000,000 over 1,000,000 plus 1 is really close to just 1,000,000 over 1,000,000. So y equals 1 is my horizontal asymptote. Now, vertical asymptote. When does the denominator equal 0? So x cannot equal -1. This is my vertical asymptote. After that, we're just going to plug in some numbers. So let's do some here to the right. When x is 0, we get 0. When x is 1, oh, I can't use 1. But this function looks like I can use 1. If I plug 1 into here, I get 1/2. What I'm going to have to do here is put an open circle. Oh, that doesn't write very well. So at 1, looks like we should have the value 1/2, but we really have an open circle there because of our original domain restriction. If I put in 2, I'm going to have 1/3. So you can see that this is creeping up. Excuse me, if I plug in 2, I get 2/3. If I plug in 3, I get 3/4. So this is creeping up towards 1. It has a little break there, and then it comes down this way. We're going to find something very similar over here if we plug in some values. So there's my rational function. We've got a couple things going on. We're going to talk about this some more as we work problems. But 2 things to keep in mind. 1, the domain of the original function, the domain of the simplified function, and our asymptotes. That should be enough to get us going. So that's it for this video. Oh, sorry, it's not. Even in odd functions, types of symmetry. All right, so we can do symmetry graphically. Even functions are symmetrical around the y-axis, odd functions around the origin. So, symmetrical around the axis, things like y equals x squared. Whereas if I fold the y-axis in half, my function will be the same on the right as it is on the left. Another example of that would be our cosine function. The right and the left sides look exactly the same. Symmetric around the origin means that something would flip from the first to the third quadrant or the second to the fourth. So this line is odd. It's symmetrical if I fold it in half across the origin. The sine function is also an odd function. So if I take this quadrant and flip it down here, it will match up. All right, so let's look at even and odd algebraically. If f is a function whose domain contains -x wherever it contains x, then f is even if plugging in a negative for a positive does not change the function. So let's look at the one we talked about, y equals x squared. I'm going to say f of x. If I plug in f of -x, that will give me -x squared, which is still the same function. So that means it is even. A function is odd if when I plug in -x, I get the opposite. So let's do the cube. Let's do x cubed. If I plug in f of -x, when I cube a negative number, I get a negative function. So x cubed is odd. Let's look at our graphs again. X squared looks like this, symmetric around the y-axis. X cubed looks like this, symmetric from opposite corners or symmetric around the origin. So let's look and see if f of x is even or odd. So f of -x would be -x cubed minus 2 times -x. I will get -x cubed plus 2x. This is the opposite of my original function. Every sign has changed, so this is odd. Oops, algebraically, that's what we just did. Graphically, we'll look at that one later. I'm not going to take the time to do the graph. We've gone long enough on this. So keep in mind, and we can actually plug that into your graphing calculator real quick for yourself at home. And go to your y equals and plug in that function, which is x cubed minus 2x, and do a quick graph on that. And it looks something like this, which again is symmetric around this origin. All right, that's it now.